Good morning, students. Am I audible? Shafam, ask your friends to join for the class. Join the class for the next session. Okay. So, any confusions from the earlier part? Cantilever beam with point load. So we have discussed cantilever beam with point load at the free end and different point loads over the span of the beam, right? So in this class we'll discuss cantilever beam with UDL. First we'll discuss cantilever beam with UDL over the entire span. Then I'll discuss cantilever beam with UDL over a short span. Okay, and we'll continue with cantilever beam with UDL plus one point load. Okay, so that will be a combination of cantilever beam with combination of different loads. One will be point load and one will be UDL. As we discussed in simply supported beam, what we did, we considered a simply supported beam with point load, simply supported beam with UDL. Again, we have considered simply supported beam with UDL and point load, right? So in the same way, we'll discuss with cantilever beam also. Okay. So I'll share my screen. Let me know if it is visible or not. Okay. My screen is visible. Please respond. Screen is visible or not?
Yes, ma'am.
Okay, thank you. So we'll discuss cantilever beam. This is the cantilever beam. Okay, fixed at one end, free at one end, and it has UDL of W per unit length. So we'll discuss this one. Okay, how many students join? 13. Please ask your friends. I won't repeat this class. Okay. Okay, let's start this class. Okay. I don't know why few students. Only 17 students. Okay, 18 students join. I hope we can start our class. Okay.
Span L fixed at end A. Consider a cantilever beam of span L fixed at end A and free at end B carrying a UDL of W per unit length over its entire span. Now let's consider a section XX at a distance of X from the free end B and consider the right portion of this section. The shear force at this section will be equal to the resultant of forces acting on right or left portion of this assumed section as per definition of shear force, according to which the shear force at a section is equal to resultant of forces either to the right or to the left of that section. But the resultant force acting on right portion of this section XX is W into length of this right portion, which is equal to WX acting downward. And since this WX lies in right portion of this section XX, it will be considered positive as per sign conventions of shear force. Hence, the shear force at this section XX is positive. Let Fx be the shear force at this section XX Fx will be equal to plus Wx, and let's mark this as equation 1, which clearly indicates that equation first follows the straight line rule, which means the shear force diagram for this span will be a straight line. Now at point B, the value of x will be equal to 0. So shear force will be equal to W into 0 equal to 0. And at point B, x will be equal to L. So on substituting x equal to L in equation first, we will get shear force equal to plus WL at point A. In order to draw the shear force diagram, we will start from drawing the baseline AB. Since shear force at point B is 0, so we will mark this point as 0. And at point A, the shear force is plus WL. So we will draw plus WL to some scale and we will join these 2 points. This will be our resulting diagram. For a clear view, the shear force diagram will look like this. And since we got the positive shear force, so SFD will be drawn above the baseline. Now let Mx be the bending moment at the section XX. The bending moment will be negative as the moment due to this load Wx will be clockwise for right portion of this section XX as per the sign conventions of bending moment. And also the beam will bend in a manner that the convexity will be at the top of the beam. It should be noted that the UDL of a section is converted into a point load acting at the center of gravity of this section. The bending moment at section XX will be given by Mx equal to minus times total load on right portion into distance of center of gravity of right portion from X. So Mx will be equal to minus times W into X into centroid of this loading which is acting on right portion of this section XX, which is equal to X by 2, and we will get a value of minus times Wx square divided by 2, and let's mark this as equation 2. Hence from equation 2 it is clearly evident that the bending moment at a section is proportional to the square of the distance of the section from pre-end, which follows a parabolic law. And since this relates to parabolic equation, which clearly indicates that the bending moment diagram for this section carrying UDL will be a parabolic curve. Now at point B the value of x is equal to 0, so bending moment at B will be 0. And at point A, x will be equal to L, so substituting L in equation 2, we will get bending moment at A equal to minus times WL square divided by 2. In order to draw the bending moment diagram, let's start from drawing the baseline AB. And since at point B the bending moment is 0, so we will mark this point as 0. And at point A the value of bending moment is minus WL square divided by 2. So we will draw minus times WL square divided by 2 to some scale, but below the baseline since the bending moment is negative. And we will join these 2 points with a parabolic curve but with a negative slope. And this will be our resulting bending moment diagram. For a clear view, the bending moment diagram will look like this. This will be the baseline AB, and the diagram is drawn below the baseline since the bending moment is negative. And this will be the parabolic curve but with a negative slope as indicated by equation 2nd. So this was all for today. For much more informative and interesting content, either to the right or to the left of the section.
So
What the
this was your cantilever beam. Again, it has two sections A and B. So you have to consider a section only one XX to find out the shear force and bending moment. Okay. So so I have considered a section XX here. So it will be the shear force will be W into X. As this is W per unit length, right? So the shear force will be W into the distance X. না আজই মেল করিম So they have considered a section XX. Okay, so the shear force will be W into X for we have discussed already that for the UDL what we take the load into the length. Okay, load in multiplied with the length. So that will be yeah. So shear force will be W into X. Okay, now at X equals to 0, at this point free end your shear force will be 0, and at X equals to L, so replace this X with the length, your shear force will be W into L. So that will be your, this will be your shear force diagram. Okay, now let's move to the bending moment diagram. Same, one section will be enough. Now with load will be W into X into the X distance. Okay, so this will be your bending moment. We know that for UDL what we do, we take half of the distance, so W into X will be the same. Now distance will be X by 2, so your bending moment has become WX square by 2. Okay, and for cantilever with UDL it follows a parabolic law. That means your curvature, your the bending moment will be some part of the bending moment will be parabolic. Okay, so see this, the bending moment at B will be 0, as there is no load and no section, the distance is 0. Now at X, at A, replace that X with L, so replace that X with L, so it will convert it into WL square by 2. So if you draw a bending moment diagram, the bending moment will be like this. As this is, see this part is this is some part of curvature. Okay, so this is a part of parabola, that's why it follows a parabolic law. As the you have got negative bending moment, that's why it is in downward direction. Okay, okay, now let's move to the another problem. Let's see another problem. The same parabola but with different UDL at some part of the beam, not entire. UDL is not given over the entire beam, over the entire span of the beam.
Ma'am,
In this video,
Ah,
we'll try to understand how. Now,
ma'am, the
yeah,
same convention, is it specific or it depends on our assumption?
your assumption, you can take, if you're, but see, if you're solving a one problem, in that problem if you're considering somewhere upward as positive, downward as negative, then it will be wrong. Throughout the beam, if you are considering upward as positive, downward as negative, you have to consider the same throughout the solution of the beam. Okay, that's up to you. You can take upward as positive, or upward as negative, and downward as positive and downward as negative. It's up to you. But throughout the question, the sign convention should be same. Suppose for the shear force, you are taking upward as positive and downward as negative. So for the bending moment also the same thing should be happen. Positive and clockwise as negative, or positive and anti-clockwise as positive and negative. Okay, it's up to you. But consider the same sign convention throughout the beam. Clear?
Okay, ma'am.
Okay. So in this beam, see, point load UDL is given over a half of the span. Earlier we have discussed UDL. Don't get confused. They have turned the cantilever beam to this part. You can take in this part, not a big issue. Okay. I got this video like this, so I've just selected randomly. So in earlier problem, UDL was UDL was spanning over the whole beam, right? Now in this beam, UDL is given over the half of the beam, half of the span of the beam. Means if your total length is 6 meter, UDL is given over the 3 meter length. Okay, so let's see. Let's solve this kind of problem. Then we'll move with UDL with point load. Okay, we'll move to complex problems. So now let's see how you can solve this kind of problems. Okay, so let's start.
so there is a uniformly distributed load acting for a half of the span length, that is L by 2, from the free end. So AB carries a UDL of W kilonewton per meter, and the we have to draw the shear force and bending moment diagram for this particular arrangement. Now the conventions that we are using for shear force diagram they are upward forces, they are considered as positive, whereas downward forces, they are considered as negative. Now shear force at A will be 0 because this is the starting point for the UDL. At B it will be W multiplied by L by 2. Now as it is acting in the downward direction, we have considered the minus sign, so it is minus W L by 2 kilonewton. Now shear force at C will be same because there is no other load that is acting between B and C. So we can say that shear force at C is also equal to minus WL by 2 kilonewton. Now we have to draw the shear force diagram. So we'll start with point A, it is 0 at point A. At point B it is minus WL by 2, remains same over the another length. So we can say that as it is below the baseline, it is negative diagram, negative shear force diagram. So at A it is 0, at B it is minus WL by 2, and at C it is again minus WL by 2 kilonewton. Now we'll have to draw the bending moment diagram for this particular arrangement. For the bending moment diagram, first we'll convert this particular UDL into point load. So UDL is W kilonewton per meter. That is for 1 meter length, the load that is acting is W kilonewton. Now this particular UDL is acting for L by 2 length. So W into L by 2 will be the total UDL length, and it will be acting at the center of this L by 2, that is L by 4. So we will simplify this particular diagram. So our UDL load is W into L by 2 and acting at the center, that is L by 4. So we can say that this is our uniformly distributed total UDL, which we have converted into point load. So it is W L by 2 and acting at half of this particular length or center of this L by 2, that is L by 4. Now the conventions that we have used for bending moment diagram, they are clockwise positive and anti-clockwise negative. Bending moment at the free end, that is A, will be 0. Bending moment at B, now we have to consider this particular point load. So this point load is WL by 2 and the perpendicular distance is L by 4, and it will produce the anti-clockwise moment about B, so it is negative. So minus W L by 2 into L by 4, so it is minus WL square by 8 kilonewton meter. Now bending moment at C, so again on the left hand side of C there is only this particular point load, so WL by 2, but the distance from this point up to point C will be L by 4 plus L by 2. Now L by 4 plus L by 2 is nothing but 3L by 4, so we can say that it will be nothing but 3 by 8 WL square kilonewton meter. Now we'll draw the bending moment diagram for this arrangement. So again all the values, they are negative. So bending moment at A is 0, bending moment at B is minus WL square by 8 kilonewton meter, and bending moment at C will be minus 3 by 8 WL square kilonewton meter. Now for AB length there is a uniformly distributed load, so we have considered this particular negative parabola or inverted parabola, and then the straight line for the remaining part of the beam, that is BC. So in this way we can draw shear force and bending moment diagram in case of the cantilever beam carrying uniformly distributed load for half of the span length from the free end. Thank you very much for watching.
So that was about the UDL with cantilever beam with UDL over a half of the span. Okay. So if you see this beam, in this question they have considered shear force upward as positive, downward as negative, right? Next, now shear force at A, this is the at the free end, there is no load, so your shear force will be 0 at A. Now let's consider a section between A and B. So when you consider a section between A and B, what will be the shear force? W into the length, right? Okay, if you replace that section, or you can take a shear force at B directly. If I take, let me change the color. If I take a section XX, What will be the shear force? My shear force will be W into this distance, right? My shear force will be W into X. Now I know this distance is nothing but, if I replace that distance with L by 2, that it will give me a shear force at B. So replace that X is equal to W into L by 2. So shear force at B will be your W into L by 2. As it is, as I already have considered the downward negative, that's why negative sign. Okay. Now shear force at C. That means at this position there is no load. So whatever I got shear force at B position, the same will be shear force at C, because there is no load. The same shear force will come to it will come to C position also. Okay. So minus W into L by 2. So with this you can draw your bending shear force diagram. From A to A was 0, at B you have shear force W into L by 2. So this is, you can replace this in questions, this they can replace this W and L with some numeric value, so don't get confused. So here you will have some amount of negative shear force, so that is that, and the shear force is same throughout this portion because there is no any other load, so the shear force is same throughout this part of the beam. So this is the final shear force diagram. As you have got negative, so that's why negative shear force diagram. Now let's move to the bending moment diagram. You can also do earlier what we have done. We have replaced the UDL with point load and place the point load at the half of the span. Okay, right? You can do that way also. As in simply supported beam, what we did, we replaced the UDL with point load to find out the support reactions. Now what they have done, they have replaced the UDL with point load to find out the bending moment diagram also. So they have considered the clockwise as positive, anti-clockwise as negative. So same at A, there is no load, so there will be zero bending moment. At B, they have considered, at that means at B, this position. My load was W into L by 2, now into L by 2 by 2. The distance will become L by 4. The distance has become L by 4. So if you multiply, you will get WL square by 4 to the 8. So this is the load, this is the distance. They have replaced the point load, right? Let me note. They have replaced the UDL with point load. This is the load and this is the distance L by 4. So just simply multiply load with distance. You will get WL square by 4 to the 8. Okay. As this is giving anti-clockwise movements, that's why negative value. Now if you consider a bending moment at C, that at this position your bending moment will be this load, the whole distance L by 2, the complete L by 2 plus this distance. Load is same, W into L by 2, but the distance will be this L by 2 plus this L by 4. So same. So if you solve this, your bending moment will become 3 by 8 WL square. Now if you draw, see, UDL was from A to B, that's why you got curved diagram. Okay, that this part is parabolic. Now from B to C, as there is no any other load, so I've got straight line as bending moment diagram. So this part is parabolic, this part is straight line. So this is my bending moment diagram. So that's what about this kind of problem. Hello? Hello?
Ma'am,
Yeah.
ma'am, how do we know that we have to draw parabolic?
See, when you will get L square for UDL, that your diagram will be parabolic. If you draw now, if you when you draw, if you see in another problem, when you join the points, you will get a curve only. For the UDL, whenever you get UDL, your for bending moment you will get a parabolic. Understood? Whenever you will get UDL, you will get a parabolic diagram. If you see the simply supported beam also, you got parabolic portion for the UDL. Go back to earlier classes, you will see for the UDL part, you got parabolic. Okay, for the UDL part, you have to draw parabola. Means curvature will be somewhat curved. Any doubts? Okay, BMC at C, explain it again. Okay, let me share my screens once again. Okay. BMC at C. Screen is visible?
Yes, ma'am.
Okay. So bending moment at C, that means at this position, right? So C, if I consider a section, let me note. So see, only I have this load. What is the value of this load? The load is WL by 2, right? So how much is this distance? Load is WL by 2. So load is WL by 2. Now into distance, right? Into distance. Load into distance. So now how much will be the distance of this load from C? So this is the L by 2. This is the L by 2. Plus, how much is this distance? L by 4. That means if you consider this one, L by 4. So this load into L by 4 plus L by 2. Understood? WL by 2, this is the load into distance. How much distance this load is acting? This L by 2 plus this L by 4. So that's why they have replaced. Now if you just simply sum up, you will get 3L by 4, and if you solve this, you will get 3 by 8 WL square. Have you understood? Have you understood?
Yes, ma'am.
Any doubts? Any doubts?
No,
Okay.
ma'am.
Okay. So write your roll numbers in the chat box. Don't leave the class, okay? Don't leave the class. One announcement has been I have to make that your second session will be from 7th of this month, 7th Jan. Okay, your second session will start from 7th of this month.
Ma'am, when it will end?
On 11th, I guess. 7th,
7 to
11th.
11.
Yeah, 7 to 11.
Ma'am, and the
Okay.
syllabus for this mechanical
Mechanics of materials. I'll text in the group. Okay, the syllabus I'll text in the group. Huh?
not making
Okay,
marks.
timetable will be out today. Okay.
Okay, okay.
So anyone left to write their roll numbers? Hope everyone wrote their roll numbers. So see you in the next class. Okay. Thank you.